Good morning. If you see the screen dancing a bit, it's not because I couldn't find the resolution, it's because you are drunk still. Okay, so I will talk today about ZFS, but before I start, as a person who attended all the VDEVs, I must say that these guys are doing pretty great job. It's excellent conference. It's almost as good as the Polish one. And I hope to see you all next year in Poland. You can even see some guys who attended last year's VDEV. Okay, so ZFS. I will start from a bit of introduction of ZFS itself, then I will try to see a few words about how it was designed, what are the layers which basically make ZFS really nice file system. So ZFS was released by Sun under CDDL license, which turns out is a very nice license for us, not for everyone, but for FreeBSD, it's quite nice. It was great. It has great design and even better marketing. People really were waiting for ZFS. I don't know, but it was really cool. And basically, the level of coolness we're keeping me working for like 2 years now. So if you want to port file system in 10 days, remember that you have to maintain it for years then afterwards. Yeah. Okay, the current state is that of ZFS itself, it was ported to FreeBSD. There is a port for Fuse framework. It's userland framework for Linux. Not only Linux, but ZFS under Fuse works only with Linux. It was ported also to macOS 10. It should appear as default maybe for system with no Leopard, or at least it will be available and it should be reliable. And parts of ZFS, mostly the parts responsible for transaction level are used in Lustre cluster file system. Basically, some bought Lustre lately. Okay. I will enumerate some features of ZFS. So it has something called dynamic striping. So you just add this to ZFS and it just balance the load using all the disks and all the bandwidth. You have write Z, which works more or less like write 5, but it doesn't suffer write 5 write whole problem. This is the problem basically if you have power failure, for example, you can end up with parity that doesn't match the data. There is also dual parity version of write Z, write Z2. It of course supports write 1. So as you can see, ZFS is not only the file system itself, but also volume manager, which is integrated into ZFS. You can find many discussions why they did that, and people that don't really believe this is the way to go. But in my opinion, knowing how many very useful things you can do when you integrate file system with volume manager, I think this was a great decision. It supports 128 bits address space. People also were laughing, why so much? 64 bits should be enough, but I think that 64 bits may not be enough. You can ask her, yes, somewhere here. If you put file system on the market, it can be there for like 20 years or more. So you should take that into account when you decide how much space you need, address space. Okay, so ZFS works using full storage model. So you don't have to partition your disks, you don't have to slice them and provision how much space do you need for each individual file system, you just add disk to one pool and create all the file systems on top of one pool. And they all share the same space, the same disk bandwidth, etc. ZFS use copy and write model, which means it never overwrites live data. So every time you write, ZFS will write to the new place and just tweak the pointers, which allows to keep the structure of file system always consistent on disk. So you don't need FS check, you don't need journaling. All the operations are built as transactions. They're committed at once every few seconds, or if there is a lot to commit, it may happen even more often. ZFS also can synchronize your data more intelligently than regular volume managers, because if you have file system integrated with volume manager, you know which data are live and which data you really want to synchronize. So you don't waste your time. If your file system is almost empty, you don't waste time in by synchronizing all the unallocated blocks. And it goes from the top of the tree to the bottom. So it first synchronizes the most important data. Those are pool metadata, then file system metadata, and then the data. So if you have some problem during synchronization, you won't end up with nothing. It will just try to synchronize the most important data first, so you'll still be able to find some data. Okay, another quite interesting feature of ZFS is unlimited number of snapshots. Snapshots are very, very cheap in ZFS. It takes less than a second to take a snapshot. And everything because it uses this copy and write model. So you can take as many snapshots as you want, and you can even create read-write snapshots, which are called clones in ZFS. You can roll back your snapshots, so it's quite useful undo operation. Especially useful when you're running, I know, FreeBSD head. You can just snapshot before the upgrade and just roll back if something doesn't work. And it sometimes happens. Also, ZFS maintains end-to-end data integrity, which means it checks all the data and metadata. It can detect corruption which were caused by anything in the way between the file system itself and the disk. And there are plenty of parts in the way, so ZFS can detect all those corruptions. If you use redundant configuration, it will just self-heal, which means it will copy good data to the. If you're running, for example, mirror, it will copy the data from the good half of the mirror to the bad half. It supports built-in compression. Currently, it's gzip and ZJB algorithms. You can set compression algorithms per file system basis. So you can, for example, keep your FreeBSD source tree compressed by not the file system which contains movies or MP3s or whatever. It can self-heal, but I will talk a bit later about that. It's endian independent. It always writes the data using native endianness, which means if you work on a big endian machine, it will always use bit endian byte order. And if you move your disks to a little endian machine, it will swap the bytes only which were written on big endian machine. And the new data will be written using little endian byte order. There is an ongoing project to add encryption to ZFS itself. Currently in FreeBSD you can just use GBD or GLI to encrypt your disks and put ZFS pool on top of those disks. Okay, this is how file system and volume model looks compared to ZFS. So as you can see, you create some volumes on top of selected disks and you put file system on the volume itself. So as you can see on the left side, you don't share all the disk bandwidth. You are limited with your file system size to size of your volume, and you have to grow and shrink by hand. And in ZFS model, it just shares all the disks, and you put all your file system. You create all your file system on top of one pool. So all the file systems share all the disk bandwidth, share all the space. So I think it's much nicer. Now how self-healing works, which is a very nice feature of ZFS. So when you're using traditional mirroring and your application tries to read some data, it asks file system for the data and then your volume manager for the data. And as you can see on this picture, the red data are bad and the green one is good. So, but logical volume manager, if it doesn't check on the data, it can tell if data is good or bad. So in this case, it selects wrong half of the mirror with corrupted data. And the sad part of this picture is that the good data are sitting in the other half of the mirror. It just didn't know what to pick. So in ZFS, on the other hand, if ZFS detects data corruption on disk, it can change the half of the mirror, read the good data, and write the good data back to the corrupted disk. So this way you can just to also log the corruption, so you can see which disks are corrupted, has corrupted data. You can run scrub to find all the corruptions, and so ZFS tries hard not to give you corrupted data, which is very nice, and this problem was ignored for many years. But it was really nice to see a ZFS mailing list and people mailing problems with ZFS because it was reporting data corruptions, and actually they had broken controllers, broken disks, and stuff like that, but they didn't know before because they were using different file system which didn't do checksuming at all. So it would be interesting to see how many strange panics occurred because some of the file system metadata, for example, were corrupted, and people just had some random panic and didn't know what was the cause. Okay, I will now go a bit deeper in ZFS design. So this is how ZFS looks from its layers point of view. So we have many layers. I will try to enumerate them and describe them in a few words. But as you can see, this yellow, blue, and red blocks are the stuff that it's ZFS internal stuff. So if you port file system like ZFS, you don't really have to tweak those much. Of course, there is some work still because this is the kernel. There are plenty of differences, but basically the most important part is to connect ZFS to FreeBSD's VFS and to Geom at the both ends. But other than that, it's quite self-contained. Okay, so we have this SPA layer. This is storage pool allocator. It's responsible for creation of pool, managing pools, and stuff like that. So this is the layer which is responsible for basically managing the pool, seeing the history, because ZFS stores all the history of all the operation you did on your file systems. So you can see what you did wrong if something happens, that happens. It can also show you all the errors it found. So you can see file system list of corrupted files, for example, if you don't use redundant configuration. So you know which files are not usable anymore. There's VDEV layer. This one is responsible for managing disks, partitions in FreeBSD basically GM providers. So this is, for example, how it looks when you create pool using one regular disk, one mirror, and write Z1 and write Z2 sets. It will just create a tree of devices like this. So this is basically what VDEV is responsible for. Then there is ZIO layer, which is responsible for all the IO requests. This is where compression, checksuming, and so on encryptions happens. And all the IO requests have priorities. For example, read requests have a little bigger priorities because you can delay reads, right? You can delay writes, but you are waiting for reads, so reads should be done earlier if possible. And stuff like synchronization is happening in the background with lower priority, so it's also very good. Okay. Next is ZFS cache, which is called ARC. It is quite nice, but this is the part which is responsible for most of the panics people are seeing with ZFS on FreeBSD, where we are running out of KVA. Because ARC is just trying to use all the memory the system has and all the KVA. And in 32-bit systems, it's even more problematic because you are limited to 32 bits KVA. And when I talked to ZFS guys, they told me that when they started to design ZFS, they thought that, well, you can just skip all those 32-bit machines because once we are done, there will be only 64-bit machines. And they were almost right, but we still have all those 32-bit machines we have to support. So basically ZFS wasn't really designed for 32-bit address space. And another nice thing about ARC cache is that it's scan resistant, so it can survive. It won't flush your cache if you perform one-time scan, for example. Okay, DMU is the layer responsible for all the transactional model in ZFS. So here you can just gather some of the IO requests and commit them as one transaction. And basically, this is a simple transactional model. The transaction is written to the disk in full, or no parts of the transaction will reach the disk or will be referenced by other parts of ZFS. So this is how ZFS handles its consistency on the disk. DSL is responsible for for handling quotas, reservation, and stuff like that, and also for snapshots, clones. Not very interesting. Okay, but ZVOL is something people confuse with regular journaling in file systems. ZFS Intent Log is not there to maintain ZFS consistency. It's only because we need fsync and fsync to work. Because ZFS transactions are committed to disk every 5 seconds by default. So it doesn't play well with fsync. That's why for all those operations that need synchronized semantics, you can ZIL will guarantee that those will reach the disk immediately. You can even use separate, faster separate disks to put your ZIL on. So if you have a large storage pool using SATA disks, you can use solid-state disk for the intent log itself, which will speed up all the synchronous operation. Another layer, ZFS Attribute Processor, it's responsible for managing all the directories and file names. It just manages name object pairs, and it's also used for other things, but mostly for file names. Traversal, this is described as separate layer because it isn't really easy to traverse live file system and live pool, but this layer allows you to traverse all the pool, all the ZFS tree safely. So you can use things like synchronization and checksum validation on live file system. You don't have to take your pool down to do it. ZVOL is the layer which basically proves that ZFS is not only file system, it also creates disk-like devices. In FreeBSD, those are just regular geom providers. So if you have a ZFS storage pool, you can either create file systems on top of the storage pool or ZVOLs, for example. You can even put UFS on such ZVOL and use ZFS snapshots if you want. So you have very fast UFS snapshots using ZVOL. ZPL is the hardest part of ZFS. This was the most pain to port because this is basically the thing which connects to VFS. Of course, VFS is a very complex piece of code, and it's very, maybe not very, but it is different than Solaris one. So this part took most of the work I did to make it right. This is the layer responsible for handling all the file system operations like rename, I don't know, change home, change mode, and stuff like that. There is the ZFS device which is responsible for communication with kernel parts. It is used by ZFS and ZVOL user tools. Okay, I will try to describe some of the features in more detail. So, in case of write 5 and write 6, used as separate layer, so you separate file system from the write. And when the write was designed, it was called redundant arrays of inexpensive disk, or that's at least one of the names. But the problem is that writing to multiple disks is not atomic operation. So you will suffer with this write-through problem. In case of power outage, you have to synchronize your entire write 5 or write 6 set, because you never know if your data match parity. And this is quite expensive. If you have 1 terabyte disks, currently it takes many hours to actually synchronize all of them. And in case of write 5, doing partial stripe writes is very slow, because you first have to read the old data, read the parity, then modify the data, modify the parity, and write those back. So to do a small write, you have to first read the data, then write them, which is very slow. In case of ZFS, write Z and write Z2, you only have full strap writes, so you never do this read, modify, write cycle. You always write all the data as one block to all the disks. And to do that, you have to integrate write Z into a file system, because only file system knows where the data starts and where it ends. So it won't send blocks of the same size all the time. So the file system have to decide where is the difference, where the one block ends and where it starts, when another starts. And of course, it also supports, mostly because of transactional model, atomic writes. But maybe I will try to describe how it works here. Okay, with P, we have parity, and D is basically data. So as you can see, you can end up with this green and blue. You can end up with two parity columns in one row, which never happens for write 5. But in case of write Z, this is the only way to guarantee atomic operations, because once you write the block, you always write the parity with the block. So if you write another block in the same row, you won't modify this parity to write this data, because it will not be atomic anymore. So in case of write Z, you can end up with a bit more space than write 5 will take. But basically, ZFS anyway gathers all the data and just sends them with larger blocks, so it's not a real problem. Okay, now I'll try to describe you how end-to-end data integrity works in ZFS. So in a regular file system, when some application reads the data, it's basically like a shipping company. What file system says, regular file system says, tells you is that here is the data, but I have no idea if it isn't broken or if it isn't maybe part of another file or something like that. So you never know if the data is yours. So you either delete your file system and your controllers and your disks, or you have to do checksumming in your application. You can checksum in hardware. So there are disk controllers that support checksumming data, but before the data reach the controller, they may be corrupted in the way there. So, for example, if you are using some network-attached storage and it does the checksumming, the data may be corrupted on the wire, and you will never detect that with checksumming. So, using this analogy, if you are using checksumming in hardware, you can only say that this is your package. It was not broken when we pick it up, and we don't know if it was broken in transit, for example. There are file systems that support checksumming, but the checksum is stored with the block itself. You can do stuff like extending this block, for example, and use the additional space to store the checksum. But the problem is that if you store the checksum with the data, you don't protect against stuff like phantom writes. So you think you wrote the data, but they never reach the disk. So next time you try to read the data, you will read the old block, but the checksum is fine, right? Because it was stored before. Also, if you try to read the data and there is a bug which basically misdirects your read, and you read different block, it will also tell you that the checksum is right because it was stored with the block. And in case of ZFS, ZFS stores all the checksum in the parent blocks. So there is no such problem in ZFS. If you try to read different block because there is some bug, it won't match the checksum because the checksum is stored in the parent block. So ZFS tries to do all those things that were on the market, but a bit better, which is very nice. And another nice thing about ZFS structure is that it is stored like a tree in a tree structure. So if you have all the checksums of all the children in parent blocks, the most highest block where the tree starts stores actually signature of entire file system, which is a very nice side effect if you are using encryption, for example. This way you have integrity verification for free. When it comes to snapshots, there are no limits on number of snapshots. And snapshots just take constant time to create. It's less than a second. It's really cheap. They don't slow down other file system operations. And when you want to remove the snapshots, it takes time proportional to number of blocks to free. Because snapshots have to maintain a list of the blocks which are no longer available in the main file system. So once you remove the snapshot, you just have to free all those blocks. And you can reach the snapshots using magic.zfs directory under your mount point. You can also snapshot ZVOLs, as I said. So you can, if you put your UFS on ZVOL, you will have very cheap snapshots. This is how ZFS tries to maintain snapshots and blocks which are dead in the main file system, but not yet in snapshots. And this is how it works. So you can see that at the top of the page we have 3 snapshots, right? Snapshot 0, 1, and 2. And this is basically how you free the blocks in snapshots. So if you can see the block B, it is only referenced by snapshot 1, but it isn't referenced by any reference counter. It's only referenced by using birth time. We are not limited by number of snapshots, so there is nothing like storing snapshot pointer in the block itself. It's only based on the birth time of block. So in this case, block B were born before snapshot 1, but also was removed after snapshot 1. So if we remove snapshot 1, the block B will disappear as well. And this is basically the same for other blocks, like block C here. Actually, block C is referenced still by snapshot 1, but basically, if the check, if block were born before the snapshot and is dead after snapshot creation, we will remove the block with the snapshot itself. Resilvering is operation which is similar to how synchronization works in volume managers. So ZFS traverses all the metadata and data and synchronize them. For example, if you connect another disk to your mirror or replace the disk or stuff like that. It does also integrity verification while it's doing it and copies only the live blocks. So you don't waste time if your file system is nearly empty. And in case of only temporary outage, it will just move all the blocks that were changed during the outage, not everything. This is ZFS status basically. I'm about to commit new ZFS. I have the patch ready. Just didn't want to do it before VDEV. And this is really a huge step because we are moving from version 6 to version 13, which basically gives us also very nice additional features which came in the way, like delegated administration, which allows administrator to assign file system tree to the user. So you can create file system for your users as your users' home directories and say that this user is allowed to do those operations on this file system. So the user, for example, can create his own file system underneath the directory, his home directory. He can create snapshots and stuff like that, which is very nice. There is also a level 2 ARC, which allows you to use small disks as additional cache. Currently, ZFS only use RAM to cache the data. But if you have large pool and you have, for example, 2 smaller solid-state disks, which are very fast, you can use those as level 2 cache for ZFS. and use all the RAM and the additional disk as the cache, which improves really significantly performance of workloads which are doing random reads of mostly static content. You can use additional devices for ZFS Intent Log. So all those synchronous operations like fsync will go to additional disk, also probably solid state disk to make it faster, or some kind of NVRAM. You can also now list all the corrupted files. There are some stability improvements. There is ZFS boot support, although it still needs some work. Currently, you can only put your root file system on ZFS, but you still have to have your /boot directory on UFS. So you at least have to have kernel and ZFS module on your UFS partition. Everything else can be on ZFS. There are also ZVOL properties. Before, you could only put properties on file systems itself. Now you can put properties on ZFS pools and snapshots as well. It also supports free failure modes now. Before, if ZFS wasn't able to write the data safely, it would just panic. So if you had non-redundant configuration and ZFS can't write the data, it will panic. Currently, you can, with failure mode wait, it will just wait for disk to reappear. So if you have only some problem with your fiber channel cable or whatever, it will wait for disks to reappear. And you can also set failure mode to continue, which means that all the writes will be blocked, but all the reads, which can be done, will be served. And it can also panic as it did before. I have also change flag support, which also needs a little bit of work still, but it is there. We have extended attribute support, which works exactly the same as it works with UFS. In Solaris, you don't have external attributes. You have stuff like FS attributes, which are file system attributes. They work a bit different than FreeBSD's extended attributes, but I created a layer which can basically translate between both of them. So if you create some file system attribute on Solaris, you will see it as extended attribute on FreeBSD. We have, I think, NFS before ACLs. This was summer of code project. We can have easily POSIX.1e ACL, but I don't know if we really want those, because I think the plan is to move to NFS before ACLs. But we can just use the same code UFS is using, because UFS is storing all the ACLs using extended attributes. Okay, so people ask me when ZFS will be ready for production use. The only problem is that ZFS currently has only one maintainer, which is not a good thing for maintainer. And basically, to remove experimental ZFS status, we need to grow at least one more maintainer, so the current one is not alone. I think this is the most important thing before ZFS could be advertised as production ready. There are still some problems, but there are a lot of people using it in production today, including me, and it just works. There are some problems with stability, but nothing significant, nothing that will corrupt your data or something like that. Okay, are there any questions? Julian?
Are all the BSD extended attributes supported, or is
Use my.
Oh, it works today, does it? Trying again. On. I'll yell.
You can use this one.
Green one was working earlier, Julian.
Yeah, green one works. This one's supposed to be on. Is it on?
Yes, it's on
yes. Okay, so try again. Are all of the extended attributes that in BSD file systems, are they all supported in ZFS, and how's the match between attributes?
Basically, we don't really use external attributes except for, I think, mandatory access control and ACLs. And mandatory access control, I think they use extended attributes directly, and we can just use them as well in ZFS.
Actually, I had a brain fade there. I meant the change flags.
Change flags. Okay. So the only difference is that ZFS doesn't support all the change flags we support. It supports a bit smaller list, something like what Darwin supports. It also supports a bit smaller list of change flags than we do. So I didn't add all those change flags because most of them are not really useful actually. But the most important ones like S-change, S-unlink, S-append, stuff like that works.
But they support the S-unlink.
Yes, yes.
That's interesting. It's interesting because we added that later.
So you were saying that it's really designed for 64-bit architectures. Does it really run okay at all on 32-bit architectures, or is it really pretty limited?
Actually, it works. It is if it is tuned down very much, so ARC won't run out of control. It just works. I'm using one of 32-bit machine in production, and it just works. It probably depends on the workload. If you really have some really heavy workload, it probably won't work very well. It will run out of KDA.
And have you tried it at all on the AMD 64 port? Or do you know people that have?
Actually, I'm running another box on AMD 64, and this one only has like 1 gig of RAM or something like that. So the memory itself isn't really a problem. The problem is address space, but also we had some problems supporting larger KDAs even on AMD 64, which was fixed recently. So even on AMD 64, we support something like 4 gigs of KDA or something like that. But it is fixed now. 6 gigs, okay.
Yeah, so I've actually been running it on i386 with 1 gig of RAM. So yeah, I've actually been running it on i386 at home for the past almost 6 months, I think. No kernel panics and 1 gigabyte of memory. So your wiki article and code work pretty well.
So if someone tells that ZFS is unstable ZFS mailing list, don't forget to answer that you are doing it.
So will it be an upgrade path from version 6 to version 13?
Yes, but I'm not sure. I probably won't publish the patch anymore because I just have the patch ready to commit. So I will just probably commit. And you are talking about 7?
I'm talking about the upgrade to 13, what happens to the data on the disk?
Basically, you can do 2 things. You can just run version 6 because the version is stored as part of ZFS information. So you don't have to upgrade, but you have ZVOL upgrade command, which you can use to upgrade your pool to most recent version. But other than that, it should be no differences. Any other questions? Yes?
I found that ZFS microphone.
Microphone.
Can I have one of those?
Bumping.
Yeah. Sorry, you got a phone.
Here, I can hand it to
I've used ZFS some in production and some in testing and stuff. What I've noticed is that its memory usage and stability seems on 386 seems highly dependent on file system size as well as usage. You know, you probably won't be creating any 12 terabyte arrays on i386 box. successfully. But for like 500, 700 gig, maybe even up to a terabyte that's not used, we've had pretty good luck with it.
Actually, I don't think it depends really on file system size, maybe more on the workload. It could depend a bit on file system size, but you probably don't have option on i386. You can run UFS on 12 terabyte file system anyway.
Yeah, we haven't, I guess, in response to that, we haven't done a lot of our, obviously bigger file systems get used more, so you could be right about that. We haven't tried to isolate usage from size so much. So you're entirely right. The 12 terabyte file systems we've created were used more than the 500 gig file systems. Maybe it is strictly a usage thing, but
I would expect so.
Will you actually have a port to 7.1, or do you put the patches in?
Not yet. First I want to commit to head, and once it will settle down a bit, because the amount of changes is basically huge. So it's few megabytes. The patch itself has few megabytes. So it's really hard to actually verify there are no regressions. So I started to work on ZFS regression tests. So I spent many weeks only on covering ZVOL command. So it's very time consuming, because the problem was ZFS on Solaris have some regression tests, but I wasn't able to form them because I needed to actually treat every regression test they had. I couldn't just change some settings and stuff like that. So it wasn't really useful, because it was probably faster to just write my own regression test. So what I could done, I think I did. We will see. I want still it settle down for a bit in head. Then I'm sure I will create patches for 7. Not for 7.1 probably. For 7 stable. Yeah. Any other questions? Okay.
To what extent does the ARC cache duplicate what the existing buffer cache is already doing, and is that a problem?
It isn't a problem because I'm skipping buffer cache entirely, which was also quite a pain, but I did it. Yeah. So you don't duplicate the cache.
So when we tested ZFS internally on 64-bit systems, this is mildly a loaded question. This PJD has heard me ask this before. We've had serious data corruption when using databases upon it. Like within 6 hours, you start seeing errors just build up in the ZVOL. Is there any work being done to address that? Because normally what I've been told is turn off ZIL. Well, if you turn off ZIL, you turn off a lot of the benefits of ZFS. So is there any work ongoing either? Is this an issue with Sun or with the code coming from Sun, or is this just a FreeBSD implementation issue?
Yeah, it's hard to say, of course, but basically tuning of ZIL is not a good option for databases, that's for sure. I can't really say about this data corruption because it mostly doesn't happen, so it's hard to say what was causing it, but there are some posts also on ZFS mailing list about some random data corruptions. I wouldn't expect it's really a FreeBSD problem because those parts are not really changed much by me.
Yeah, I think some of it may just be inherent in the ZFS code, because we found out recently that even Sun tells you not to really run MySQL or Postgres on a ZFS database. They say make a UFS slice or whatever for it.
But this is probably because of performance reasons.
No. Oh, okay. Maybe for performance reasons.
Because even with ZIL and even with ZIL on additional like solid state disk, it probably still is slower than UFS because database basically overrides the data. And in the case of ZFS, we always write to new place.
I was at Lisa last week manning the PostgreSQL booth, and a user came up and said, listen, we're having this real big problem with ZFS and Postgres. After we added a few million rows to the table, performance slows down on ZFS, but it doesn't happen on UFS. And his initial theory was it was the copy on write. And what Peter's saying and what you're saying makes me think that that may be the cause. But I told him to talk to the PostgreSQL performance mailing list, and we'll see what comes out of that, because it may be something as simple as not vacuuming the tables often enough, or indexes that get out of date or something. But we'll find out.
Yeah, but it could be ZFS call, because with copy and write, it can become fragmented over the time. It won't be the problem when we are all migrated to solid state disk, right?
So is there a defragment?
According to Peter.
Peter?
Yeah.
Chris?
There have been a lot of reports of data corruption on some SATA disks, which maybe, so the ones I've seen seem to be actual driver issues, and it's being detected by ZFS, and ZFS is actually repairing the corruption that's happening in the driver layer, but that's actually a driver issue or a hard disk.
Yeah, I mean, after what normally happens is after 6 hours, it gets to a point where it can't recover the errors fast enough.
Okay.
So we tried it with a 3-word card. We tried it doing just basically disks directly onto the motherboard, where it has like 8 ports on the motherboard, 8 setup ports on the motherboard. We've also tried it on another system just to try to eliminate sort of, oh, it might be either bad disks or whatever. I mean, we could be wrong. We could easily have just gotten a really bad batch that week. So.
Speaking about freeware, I found freeware polo t-shirt yesterday. If someone lost it, just contact me. A side note.
Maybe we should talk more about this.
Okay. Yeah, I'll be here for the day or something, so crap.
And questions of Pawel. So if you have ZIL disabled, why am I still getting 144 ZIL clean threads? I don't know answer right now.
It could be that that we can just turn them off, but basically, basically turning off ZIL shouldn't be even an option. It should always be on, actually. There is a syscontrol for that. Yeah.
As you know, there are some deadlocks with low memory conditions with ZIL enabled. So.
Yeah, and this is probably only because this is why you have this syscontrol to turn it off.
Sure.
But other than that, from functional point of view, you shouldn't turn on ZIL.
Right.
You should never turn on ZIL. Any other questions? Warner.
Don't worry, this one should be easy. What's the current status of using ZFS for your root file system and booting off of ZFS?
Jakub was working on ZFS boot. Currently, you can use ZFS on a root file system. I'm using it on my laptop. That's not a problem. And then you just need small partition with /boot directory in your kernel, ZFS kernel module. To boot off ZFS, a lot of work was done already. So I think it's only some few bug fixing away to make it really work.
Okay.
But again, we don't have ZFS supporting sysv installs.
Okay, I was just curious.
Yeah, but there is a lot of
cost drives on laptops. Perhaps people know about some of my experience.
So,
and I was thinking ZFS might be a little more robust. So, thanks.
I don't think the ZFS is